In the last video, we talked about conservation of mass. Now, as if that wasn't exciting enough, now we are going to talk about conservation of energy for a control volume. So essentially, we're going to kind of add to the material that we just talked about. Now, to get started, let's go ahead and draw a picture. So let's just say we have something that looks like this. And let's put a dashed line to indicate that this is going to be the boundary of our control volume. Looks like that. We've got an inlet here. We've got mass flowing in. Let's call that Mn dot. Now we're also going to have an outlet where we have mass flowing out. So let's call this M exit dot. That'll be our exit, and that dashed line is our control volume boundary. Now what we're going to have on here, let's say we're going to have some energy transfer due to heat. And in this case, we're going to use Q dot, and I'll explain that in just a second. And then we're also going to have energy transfer from work, and now we're going to be looking at the time rate versions. So let's put W dot, and I'll explain that in just a second. So this is kind of an example of a system with one inlet, one outlet. Let's look at conservation of energy now. Let's write it out in word form, and then we'll put it in equation form. We're going to say that the time rate of change of the energy contained within the CV at time t, remember these are all going to be time specific, is going to be equal to the net rate at which energy is transferred in by heat at time t, minus the net rate at which energy is transferred out. Let's put the out here. Out by work at time t. Okay. So in the old examples, when we had a closed system, we weren't really looking at a rate because we didn't really have anything to deal with time in our equations. Now we've got a mass flow rate, and that gets us seconds in our equation. So in our old energy balance equation, we just had Q and W. Now that we're looking at rates, we're going to switch it over to Q dot, W dot. Now we've got this. Now I'm missing one more thing. I'm out of room to write it, but we're missing one more thing. We've got all of this mass flowing in and out. Now there is energy associated with that. Okay, we have to add that in. So we are going to put plus, this goes at the end here, I'm out of room, so we'll move it down here. We're going to have plus the net rate of energy transfer into the CV that accompanies mass flow. So now we have three terms. Before, we only had two terms on the right. We just said Q and W because we didn't have any mass flowing. Now that we have mass flowing, we have to have this. Now let's get our equation in actual equation form. Left side is going to be the time rate of change of energy in the control volume. So this capital ECV is the energy contained in the control volume. That is going to equal Q dot. So let me get this. So this here goes with this. Q dot goes with that. This next term where we have the net rate at which energy is transferred out by work, that's going to be, you guessed it, W dot. So this one is for that. And this part here, we're going to have plus. This is going to deal with our mass flows. This one is going to be longer. This one we're going to have mi dot, so this is for the inlet, times ui plus vi squared over 2 plus gzi minus, now we gotta look at the exits, me dot times ue plus ve squared over 2 plus g times ze. This is going to be equation 1. So these two together are from this. Now if you look at these in the parentheses, that should look familiar from what we talked about before. We've got internal energy. This, if you look, it's kind of from kinetic energy. Then this, if z is elevation or height, this would kind of be like our potential term. Okay, so now we have that longer equation. So this will be the equation we're going to be using now that we have mass flowing. And again, if there is no mass flow, just looking at this equation, this would go to 0, this would go to 0. So we could say that dEcV over dt is equal to q dot minus w dot. All right. So now we have that. And we'll circle the equation later. This is for one inlet, one outlet. The main equation we'll use will be set up for multiple inlets, multiple outlets. So we won't circle this one. We'll add one more thing in just a second. Now let's go over evaluating work. If matter flows across the CV boundary, our control volume boundary, then we've got work being done. Okay? I don't know if y'all can hear in the background, but there is a tornado siren going off. So if you hear that, that's what that is. It's the weekly test. There's not actually a tornado. Okay. Now what we're going to do is we're going to separate work into two pieces. Okay? Work is going to be associated with fluid pressure as mass is introduced at inlets and removed at exits. That's going to be one of the pieces that we're going to have. The other piece we're going to have is all other work. This is going to include work from rotational shafts, electrical devices, anything that's external is going to get lumped into this second piece, and we've got a variable for that. That is w dot CV. Okay? So we've either got work associated with fluid pressure from our mass being introduced and removed, or we have everything else. So those are the two parts. Now remember, W dot is the dot product of force with the velocity vector. So now if we use that fact, if F is written in terms of pressure at the exit, then F dotted with V is going to be the pressure at the exit times the area of the exit times VE. So that's what we'll get. This is just an equation for our work, essentially, at the exit. So now, if we know that, we can then say that the work that is done by the normal force due to pressure at the exit is going to be PE AE times V. Then at the inlet we would have something similar, except for we'd have different subscripts. We'll have the pressure at the inlet times the area at the inlet times the velocity at the inlet. Okay, and again, these just come about by doing that dot product with the force. Remember, the force is going to be normal to our boundary, and then the velocity vector. And all we did was replace F with the pressure times area. Now that we've got these two established, let's get our total work, because remember we said we were putting it into two pieces. So our total work will be W dot. That's going to be equal to the work from all the external things. So if you have a rotating shaft, for example, that work is going to go in here, plus our exit. So the work done due to mass being moved out, minus the one at the inlet. So PI, AI, VI. Okay. So here we've got work being done by the system because it's forcing mass out. So that's why we've got this positive sign. And let's put mass going out. Then over here we have a negative sign because something is forcing that mass into the system. So we'll say work done on the system. We've got mass coming in. Okay, so that's why we set up the sign notation like it is right there. Now we have our total work, or the rate at which work is being done. Remember, we're going to expand on this a little bit. Remember, m dot is equal to volumetric flow rate over V. So notice we've got AV in here. Let's solve this equation for AV. So AV is m dot times specific volume. Let's replace A and V in this equation with m dot and V. That'll give us W dot equals WCV dot plus ME dot times PE times VE minus MI dot PI times VI. Now these terms right here, this one at the exit, this is called flow work. So if you ever hear anybody talk about the flow work is such and such, that's just this product right here. This is going to be what's called the flow work at the inlet. Let's call this equation 2. Now we're going to go ahead and get our final version of our new energy balance equation, if you want to call it that. Let's take this equation 2, plug it into that longer equation 1 I had on that last sheet. And if you do that, you're going to get time rate of change of energy in that control volume. That's going to equal QCV dot minus WCV dot plus MI dot. Now in the parentheses, we're going to kind of expand things out here. We're going to have UI plus PI VI plus capital VI squared over 2. Remember that's velocity, plus GZI, and then subtract this same thing but with the E for the subscript for the exit. So we'll have ME dot times UE plus PEVE plus capital VE squared over 2 plus G times ZE. Now you get that. Now if we look at this equation, so take a look at that equation, and specifically I want you to look inside the parentheses. Do you see anything that we could replace there? Actually this, I just noticed an error. This should not be velocity. That's a little v right there. It'd be hard to answer the question when I've got the wrong symbol in there. Let's look over at this one. Here we've got U plus P times V, little v. If you remember, this was enthalpy, right? So if you remember, H was U plus P times V. That's what we've got here. So let's replace this with enthalpy. Okay, that'll be a lot easier. Enthalpy is given in the tables. That way we don't have to worry about having to find U, P, and then V. All right, we'll just find enthalpy instead. So let's replace that with enthalpy. So we're going to have dEcV dt equals QCV dot minus WCV dot plus MI dot times the enthalpy at the inlet plus VI squared over 2 plus GZI minus ME dot times enthalpy, this is specific enthalpy, at the exit plus VE squared over 2 plus GZE. Now we shortened it a little bit, so that's good. This is for one inlet, one outlet. We're not always going to have one inlet, one outlet. A lot of the times we will have multiples. So let's do our final equation, and this one will be for multiple inlets and outlets. So easy change, we just need to add in a summation or two. Left side stays the same, and it's going to be equal to QCV dot minus WCV dot plus the sum over all of the inlets of MI dot times HI plus VI squared over 2 plus GZI minus summation over all the inlets, or exits, sorry about that, of ME dot times HE plus velocity of the exit squared over 2 plus GZE. This will be our final equation. You probably thought we would never get there, but there it is. That'll be equation 3. All right, one more thing we need to talk about. Let's look at how steady state will affect this equation. Remember, if we have steady state, all properties are unchanged with time. Time is the key word there. That means if you look in that equation we just wrote, then we're going to have the time rate of change of energy. This has to be 0. Okay, so that gives us a simplification. We can rearrange that equation 3 then to get the following. So we'll have QCV dot plus, let's put the inlets over here. So sum over all the inlets of MI dot times HI plus VI squared over 2 plus GZI. That's going to equal W dot, this is WCV dot, plus the summation over all the exits of ME dot times HE plus VE squared over 2 plus GZE. This here will be the energy rate in. This over here is energy rate out. So now we have that. Now for one inlet, one exit, what we're going to have is the case that MI dot is going to equal ME dot. So let's just call it M dot. So we'll simplify it. Okay. Now, using this simplification from equation 3, let's get our final version. We can write that 0 equals QCV dot minus WCV dot plus M dot times the change in enthalpy, so between 1 and 2, plus v1 squared minus v2 squared over 2 plus g times z1 minus z2. So that's one version. Now sometimes you're going to want to have q dot over m dot. So let's write that version out also. So left side will still be 0, and then we've got qv dot over m dot minus wcv dot over m dot plus h1 minus h2 plus v1 squared minus v2 squared over 2 plus g z1 minus z2. These will be our equations for steady state. Remember, this is for steady state only. So don't try to use it unless you have steady state conditions. All right. And by the way, we just put this up here so you could see if you ever hear the energy rate coming in, you know that that's this term. Energy rate going out would be this term right here. All right, but these will be the main equations we use for steady state. Okay, other thing I want to make sure we remember is this fact here. All right, guys, so that's the end of the derivation part of this section. Next video will be an example. See you then.